Okay, this video is all about the boundary behavior of waves. Your objective as you watch this video is to understand how properties of a wave change when they encounter a boundary or a change in medium. Okay, this video is going to go into detail with the last part of that Slinky lab kind of illustrated. Okay, there's two different types of reflection that happen to a wave. One is called a fixed end reflection. The animation that you are watching is an example of a fixed end. Notice that black dot. Okay, that black dot represents the part of the wave that would be like anchored down to something. Okay, notice the wave as it travels across the screen from left to right. Okay, I want you to look at a couple different things as you stare at that animation. First, how does it look like the speed of the reflected pulse compares to the speed of the incident pulse? Remember, the incident pulse is what's showing now. The reflected pulse is what happens after it bounces off that boundary. Okay, hopefully you can tell that the speed of those two pulses are the same. So how long it takes to move left to right is the same amount of time that it's moving right to left. Okay, let's look at a few other things. Okay, how does the wavelength of the reflected pulse compare to the wavelength of the incident pulse? If you're having a hard time seeing this one, take out a ruler and hold the ruler up to the screen. Can you see that the wavelength of the wave doesn't change just because it bounces off that boundary? Well, as you watch that animation, something is definitely changing. What is changing is what we call the polarity of the wave. Okay, it travels as a crest, it hits that boundary, and now it reflects back as a trough. Okay, what we see is that the wave has inverted when it hits that fixed end. Okay, why does it inverse? Can you think of how Newton's third law explains why that pulse all of a sudden inverts and goes the other way? Hit pause on this video and write down your answer. The other type of reflection we can have is a free end reflection. Okay, notice on a free end reflection, as the wave hits that boundary, those particles are free to move around. So in other words, there's nothing anchoring them or holding them down. Okay, I'm going to ask you the same questions. As you watch the incident pulse, look at what happens as it reflects and travels back towards the left. Okay, look at the speed first. How does the speed of the reflected pulse compare to the speed of the incident pulse? Okay, do you notice that it's the exact same speed? So just because we're hitting a boundary doesn't mean that our speed is changing in this example. Okay, what's different about this free end reflection versus the fixed end reflection is that the wave does not invert. Okay, notice how I have a crest traveling towards that boundary. It reflects and it travels back as a crest. What would happen if it was a trough? You guessed it. If it was a trough, it would travel back as a trough. In a free end reflection, there's no action-reaction pair that would cause the particles of that wave to invert. Okay, there's no force causing it to change its direction of motion. Okay, instead, the wave is just free to move and bounce back once it hits that boundary. Okay, the free and fixed end reflection are just kind of two different types of what happens when we hit kind of either a fixed boundary or a free boundary. We can also hit boundaries when we change mediums. Okay, the animation that we're going to watch right now is going from a low density medium to a high density medium. In the lab you did, that would be like going from the Slinky to the Snaky. The reflected pulse is what's going to travel back towards the left-hand side of the screen. The transmitted pulse is what continues to move towards the right. Okay, what I want you to look at first is the amplitudes. Okay, so look at how the amplitudes of the reflected and transmitted pulse compare to the amplitude of the incident wave. Okay, here's the incident wave. What did you notice about the transmitted pulse first? Did you notice that the amplitude actually decreased? Okay, let's look at the reflected pulse next. Notice how the reflected pulse also has a decrease in amplitude. Remember, amplitude corresponds to the amount of energy traveling in a wave. Hopefully it makes sense to you that the energy is actually being split between what's traveling forward and what's coming backwards. Okay, look at the polarities or the direction of the amplitude. Okay, notice how the transmitted pulse does not invert, but the reflected pulse does. When we hit this more dense medium, it's acting as if it's a fixed end. Something heavier is able to push back on something lighter. So we've got Newton's third law in action right here at the junction, causing that reflected wave to invert as it travels backwards. Okay, look at the wavelengths next. Okay, so look at, again, the reflected pulse is what comes back. The transmitted pulse is what goes forward. Okay, on the transmitted pulse, can you see that the wavelength is what decreased? Okay, looking at the incident pulse and the reflected pulse, the wavelength actually stays the same. Okay, one more thing I would like you to notice. What do you notice about the speeds of those pulses? Did you notice that the speed, once it hit the more dense medium, slowed down, but the speed in the incident medium remained the same? If not, hit rewind and watch it a few more times. Let's go the other way. Let's go from a high density medium to a low density medium. Okay, the high density medium again would be like the snaky that you used in the Slinky lab, and the low density medium would be like the snaky. Okay, let's look at the amplitudes first. So how did the amplitudes of the reflected and transmitted waves compare to the amplitude of the incident wave? Okay, so here's our incident wave. Notice how the transmitted wave has a much higher amplitude than our incident wave. If we look at the reflected wave, the amplitude is smaller. Okay, the amplitude gets bigger in our transmitted wave because it's easier for those particles to move. So the same amount of energy is able to displace those particles from their equilibrium position quite a bit more. Okay, look at the polarities. Okay, so our incident wave is traveling as a crest. Our transmitted wave is also a crest. Our incident wave is traveling as a crest. The reflected wave is also traveling as a crest. When I go from a high density to a low density medium, that's almost like a free end reflection. There isn't enough force at that junction to cause the reflected wave to invert. Okay, if you look at the lengths, okay, so the length going from the incident pulse to the transmitted pulse has a much greater length. The reflected pulse, the length of the wave stays the same. Okay, to kind of summarize what's going on, okay, the boundary behavior is what happens when we meet any kind of a junction. Okay, so it could be just being attached to a pole or being allowed to move freely, or it could be changing the densities of the materials. The wave speed is always going to be greater in the least dense medium or the least dense rope. The wavelength is always going to be the greatest in the least dense rope. The frequency of a wave is not altered by crossing of a boundary. Again, the frequency of the wave comes from the source. So if it was the Slinky, it comes from how many times you're creating a wave in your end of the Slinky. On the animations, it's just how often that wave was repeated on that animation that you were watching. The reflected pulse, again, the one that bounces back, becomes inverted when a wave in a less dense rope is heading towards a boundary with a more dense rope. We're able to get an action-reaction pair when this happens, and there's a force that's going to cause that inversion. The amplitude of the incident pulse is always greater than the amplitude of the reflected pulse. Okay, again, amplitude corresponds to energy. So the incident pulse always has the greatest amount of energy. When we hit that boundary, some of that energy is transmitted and some of it is reflected.